Hello, another lesson today on calculus, continuing on our topic of maxima minima. So calculus, maxima minima, one of, if not the hardest topic in 2-unit advanced syllabus in Year 12. So last video, I basically proposed a framework to doing maxima minima. Basically, if you look through the number of questions that I've looked through, you'll find that most maxima minima questions has two parts. The first part is basically to prove the equation to differentiate Yep. So basically that involves you either using measurements, so volumes, areas, and perimeters, etc., similar triangles even, to basically derive an equation for you to then differentiate in part two. So part two. So generally speaking, mark-wise, part one is ranges from 2 to 4 marks approximately. Part two, anywhere between 3 to 4, maybe even 5 marks. And you'll see today in an example from James Roos, there's a 5-marker, just because not only do they want you to solve it, they then want you to answer a subsequent question within that mark allocation as well. So part two, generally speaking, is basically find the max or min of a variable. So maybe you're trying to maximize volume or minimize area, etc., etc. So within part two, it's very important for you to identify 3 to 4 steps. First one is basically to differentiate the equation that you've derived in part one, solve. So once you differentiate, you solve, because when you're trying to find maximum minimum, you basically solve a differential equation, solve, and then you test for max or min. And by that, there are either use the second derivative or table method. General rule of thumb is that if it's easily differentiable, use the second derivative. Otherwise, use a table method approach. And last but not least, sounds obvious, but answer the question. So if the question is asking you to find the value of x, that's what you do. Or if sometimes they might ask you to find the area that is maximum or find the volume that is minimum, then you basically use your x or your radius to answer that question. So guys, that is the framework as I basically set up last week. So let's now apply this framework to, once again, a few past paper questions that I've sort of prepared. So we'll start with a question that is wordy in nature. There's no diagram, which in itself sort of implies that you should draw a diagram, from Barker, so 2014. So in this question, it sort of starts with a 6-meter piece of wire, so long piece of wire. It's cut into 3 parts to form 2 congruent or identical squares and a circle of radius r. So you can see classic question where there's part 1, prove this formula, and then part 2, find the exact value of r, which makes combined area a minimum. 2, 3 marks allocated respectively. So a classic question in terms of structure, but slightly different in terms of how we go about it, because A, there's no diagram, and B, well, actually no, it is a classic question that it deals with measurements. So let's go there. So part 1, very smart thing to do. If there's no diagram, draw yourself a diagram. So in this question, we're basically saying there is a 6-meter length of wire, and it is cut into 3 parts, where the first 2 parts are used to create 2 identical squares, and the third part there is used to create a circle. So if we can sort of picture, this piece here is used to create a square, this guy here, create a square, this guy here, create a circle. Right? Now, let's pretend that each square or leg in this question each side here be x. Yep. Now, and then it tells you in this question, and let's use it because it says the radius of the circle is r. Yep. Now, this is interesting because remember, in terms of our framework, the hardest thing about part one in both of these parts is part one, we have to prove an area in this case where it only has one variable, and that variable is r. You can see if I want to derive an area for these three shapes, I'll have x and r. So somewhere down the line, I'm going to remove x with some other factor they give me, and that other factor in this case is definitely going to be the 6 meter length of wire. So before I do that, let's quickly jot down a combined area. So that's x squared for the first square, and there's two of them, so maybe for completeness of working out, plus x squared and plus pi r squared for the circle. Now, so if I clean this up by grouping my like terms, you can see here I have an x squared in my area, right? Which currently I need to basically remove, right? Now, how do I remove it? If I use this fact over here, right? I know that if this was x for this side of a square, then wrapping around the perimeter, this length from here to here would be 4x. And same thing here to here, that would be 4x as well. And I know that using my perimeter of a circle, this guy here would be 2 pi r. So then the sum of the three parts, 4x plus 4x plus 2 pi r is going to give me 6 meters. You can see there, if I basically make x the subject, so what I'll do, actually no, I won't chuck it over yet. Do that divided by 2 would be a smart way to go about it. So 4x, and maybe simultaneously chuck it over 3 minus pi r, divide the 4 down. Now I have an expression, 4x, in terms of r, which I am going to plug into that guy there. And just have a quick glance upstairs, 3 minus pi r, perfect. You can see 3 minus pi r, when I sub the 4 in and I square it, becomes 16, multiplied by 2 becomes 8, perfect. So then therefore, I'll get a equals to 2, plug in the 3 pi r on 4. Your teachers love seeing the substitution, so please show them this step where you basically plug in the number instead of just plugging it in and simplifying it all in your head. Show that substitution piece. Therefore, a equals to now, then cleaning this up, 2 and 16 cancels out, so put brackets there, 3 minus pi r squared, or 1/8 plus pi r squared, perfect. And that's part A, or part 1 rather. Right, pretty straightforward, right? And it follows the framework to a T. Yeah, basically there's two variables at play. I need to make one of the variables a subject using a given fact, sub it in, get what I want. Now, even if you couldn't do part 2, I say this to my students all the time, if you can't do part 1, use it to do part 2. So if you couldn't prove that, that's fine. You still can use it to prove maximum and minimum. Now, so the framework basically says 4 points, right? Differentiate, solve, test for max min, answer the question. Now, what is the question? Find the value of r. So that's pretty easy, right? So once I test for max min, that is my answer. So let's pop upstairs over here. So for part 2, I have the area looking like 3 minus pi r squared all over 8 plus pi r squared. All right, let's do this. So differentiate, solve, test for max min, and then answer the question. So I'll start off with this guy, which is where I ended in part 1. Now, what's the best way? Let's just differentiate it as it stands. So dA, dr. Now that's chain rule, bring down the 2. Becomes 1, yeah. I guess full. And then multiply that by the derivative of the inside, which is, in terms of r, that's multiplied by minus pi. And then plus. So I guess when people try to differentiate this, a lot of the times they're a bit stuck It's because of the pi. The pi is a bit distracting, but it's just a constant, right? So if I clean this up, this is my derivative. So let's see, clean it up. You know what? I don't need to, but I think I will common denominator everything here and expand probably just to get this up and running. So if I sort of put negative 2 pi 3 minus pi r, that's this guy here on 8, and then I'll common denominator this 16 pi r all over 8. Yep, so actually before I set that to 0, let's just clean up here, right? Let's just clean up. So I can see value of r there, which I am going to factorize. And just to clean up my algebra a bit, so I got negative 6 pi plus what looks like 2 pi r squared. No, 2 pi squared r plus 16 pi r all over 8. Yep, so I'm almost there. I mean, I can do 2 more things to clean this up. Divide everything by 2, top and bottom, and then maybe factorize the r out. So I sort of get like minus 3 pi plus, so the 2's go away, maybe the pi as well. So maybe I'll go pi r outside of, so pi r and 2's gone, so that's just pi plus 2's gone, so that's 8. And that's r all over 4. And that is my derivative. So I suspect out of 3 marks, getting the derivative itself might be 1 mark. Yep, now I'm going to solve that equal to 0. So you can see when I solve it to 0, the 4 goes away, the 3 pi goes over. What am I trying to do? Actually, I've done something wrong there, haven't I? When I factorize it, that's not an r. So let me just quickly fix that. It's actually a 1. Let's see, take out the 4, take the 2, pi's out. No, 2 pi r, so that's 8 actually. Right, 8. So let's see. So over here, I'm setting this to 0, so the 4 goes away, and I got pi. If I throw the 3 pi over to the other side, I get pi plus 8 equals to 3 pi. Cancel out the pi's. What am I trying to do? I'm trying to make r the subject, so it looks like a simple case of just dividing over pi plus 8. Yep, have a quick check on that. Looks fine. So now, let me just check the rounding. It says find the exact area, so that's perfectly fine. I'm going to have a quick glance at this. This looks to be, it looks messy as, but it's a linear expression, which means when I test for max min, very easy just to differentiate again. So let's test for max min. So I think I'm going to run out of space. So can I click and drag a space over here? So let's test for max min, whereby I won't need the extra space because I don't need, once I test for max min, that is my answer. I don't need to, I'm just finding r. So when I test for max min, I'm going to differentiate again over here. So d squared, dr squared, constant goes away. That's a constant, that's r, so it becomes just pi plus 8 on 4. Now I'm hoping it's a minimum because that's always a positive value, right? Minimum, perfect. Yeah, because pi's positive, that's a fully positive value, right? It's always greater than 0. Therefore, minimum area when r equals to 3 on pi plus 8. Sweet. And centimeters, is it? Meters. Which is my final answer. That answer happened faster than I thought it would, which is, means highlight. It came on faster than I thought. Beautiful. So how was that? That followed the framework to a T, right? Where part 1, find the equation. Part 2, differentiate, solve, test for max min. And then I answered the question because it's just find the exact value for r. So pretty sweet. Let's do another one. So I don't need this extra space. Now, a classic hard question, you know, hard inverted commas. One of the last, classic last questions in an advanced paper. It's when there's a maximum minima and there's a 3D shape. Now, they can muck around with all these shapes where they either put in this case, a cylinder in a sphere. They can put a cone in a sphere. They can put a cylinder in a cone. They can put sphere in cylinder. The combinations go on and on. All of them sort of follow a pretty standard framework. And that framework, once again, you can see part one, find the volume, and this volume. Now we know that volumes of a cylinder normally has two variables, right? On the other side, it's got R and H. This one only has X, which looks to be the radius. So somewhere down the line, I need an expression for its height in terms of its radius. Yeah? So that's part one, 2 marks. And then part two, classic, in this case, 4 marks of differentiate, solve, test for max min, answer the question. Now, just to be clear, what do I have here? I got diameter of 10. Sorry, where's this question from? It's from PLC, the one in Pimble. So 10 meter radius. Now, it's always dangerous for a lot of students when there's information given in the words, but it's not in the diagram. So the diameter is 10. Now, this diameter of 10 for a sphere is actually quite a powerful fact. And you'll see it here. Right? A lot of people don't really know how to use it. I mean, a dead giveaway for those that know what they're doing is when you're proving this fact here, you can sort of see this guy here. I mean, what does that look like? For those that know, that sort of looks like Pythagoras, doesn't it? Looks like the one of the sides of Pythagoras where you square root it. So we're definitely going to be using Pythagoras to help us out here. So this is what I'm going to do. On this diagram, I'm just going to show you the game for part one. Let's do part one, where we're going to prove this volume. And part two, just find the dimensions of a cylinder. So that's radius and height, right? And dimensions normally. Maybe I'll be explicit with that and say, so find R equals a question mark and H equals a question mark. Yeah. So in this diagram, where can I use the radius of a sphere? So generally speaking, right, if you think about how you're going to do this, I've got X, right? That is the radius. Beautiful. I need height. Yeah, that's missing. Yeah. So actually, before I do this, before I give away the game, let's start with volume of a cylinder is pi r squared h, right? We start here. Everything starts here because you can see I don't want h in there, right? I want something else. And also, they've replaced r in this question with x. This one here, question mark. Let's find that now. So let's come back to the question itself. You can see if this distance here, which is the radius, that's x, I can utilize the 10 meter diameter, which looks to be, now let me think, 10 meter diameter, right? Diameter. Yep, that's perfectly fine because that there is 10, which means that if that's 10, let me see, what's the best way to do this? Maybe, I'm looking at this here, I'm actually not going to use Pythagoras. Oh, I thought about using Pythagoras. Normally, I would just use Pythagoras on the small one, but because they want 10 over here, and they want h over here, then I can actually say this is 2 times the radius, right? There lies my Pythagoras, which gets me that side. You can see, right? By using this Pythagorean triangle, let's have a look, right? I'll do it over here in green. It's perfect. It's exactly what I want. 2x and 10 by Pythagoras, 10 squared equals a h squared plus 2x all squared. Therefore, h squared equals to 100 minus 4x squared. Perfect. H equals to square root. It's always positive because it's the side. It's a length. And there it is, guys. I have my equation, which I will replace into here. And I can conclude, therefore, volume of x as a function of x equals to, I won't fit it in that space there, so I'm just going to move it over here a bit, equals to pi r, so not r now, it's x squared, and then square root of 100 minus 4x squared. I mean, pretty stock standard there, right? I guess the trickiest bit there, I sort of went in automatic mode where automatically I would basically draw a right angled triangle over here. But in this case, it's just easier given the numbers. I mean, theoretically, if I use that blue, I still get the relationship. I just need to clean up the fractions, etc., to get that. But let's just use a bigger triangle in this case. Perfect. All right, man. Let's move on. Part 2. So part 2, once again, classic in terms of the framework. Let me just shift this information. In fact, maybe I'll move it down here. Buys me a lot of space. So we always begin, right, with the equation that they gave us. So that's volume equals to pi x squared square root 100 minus 4x squared, right, as a starting point. And I'm just going to differentiate. Yeah, just going to differentiate. Looks like when I differentiate, and I wonder if that's why it's 4 marks. Bit of product rule there, right? That's u, that's v. Yeah, so off to the side, u dash, pi's a constant, so that's 2 pi x. And b dash there, what's that? Bring down the half. Minus 1 to the power multiplied by derivative of the inside, what's that? Minus 8x. Clean that up, the 8 and 2 goes away, so that's negative 4x on the top. Bring down the negative index downstairs, put a square root. That's my derivative. That's v dash. Yep. So slightly complicated derivative, which I'm hoping that's what it's telling me, is that when it wants me to test for Maxima, I'm probably going to use the table method. Let's say u dash v plus or minus in this case, because v dash is negative, and that times that, so it looks like it's 4x times pi x, so it's just minus 4 pi x cubed all over minus 4x squared. All right, guys, that is my first step. Differentiate. Now, let's solve this. Bit of a monster, but not too bad. Bring this guy over. You can see it's a bit of a monster, but when I times it to both sides, the square roots are the same, so you get some nice whole numbers. So let's have a look. So bring this second fraction over. Minus 4x squared equals to 4 pi x cubed all over minus 100 minus 4x squared. Perfect. Times this guy up. You know what? Let's look forward. So maybe divide that by 2 pi. 2 pi leaves 2. Yep. So you get like x times 100 minus 4x squared, because the square root times square root goes away. And on this side it's just 2x cubed. And that, so what's that? 100x minus 4x cubed equals to 2x cubed. Yeah, let me have a quick glance, make sure I'm on the right track. Looks to be fine. Let's move everything over, please. Maybe move everything over to the right. So 0 equals 6x cubed minus 100x. If I factorize 2x from there, I get 3x squared minus 50 equals 0. Yep. And it looks to be, I mean, you can solve that. You get x equal to 0, which obviously isn't right because I want a positive number, and it'd be plus minus root 50 on 3, which negative once again is wrong. So I only take, so in this case, you can go therefore x equals to root 50 on 3, since x is greater than 0. Yeah, only. So this is the one we're going to test for max min. Now, if you punch this into your calculator, which I actually have a virtual one here, I would suspect, actually, let's go square root. Was it 50 on 3? So it's approximately, x is, oops, pen tool, x is approximately 4. Maybe 1 dp and 4.1. Yep. And I'm going to use that to test for maximum. I'm not going to use the second derivative because look at this monster here. If I wanted to differentiate this again, it might take me a while because it looks like a product rule quotient rule. Bit nasty. So instead, I'm just going to use a table method on this guy. So actually, let me set the working out perfectly. So test for max min. Now I'm going to do something really bad in terms of working out. Your teacher might deduct a mark here, but in the interest of time, because it's just calculator work, when you do the table method, a lot of schools would demand that you actually punch it in and put in the decimal place. If I said to you that's x and this was 4.1, and let's say this is 4.0 and 4.2, a lot of schools would demand that you actually punch these numbers in. I am going to shortcut it because I know when I type in my my maximum minimum point, it's always going to be 0. Now, this is almost like a check, but because they're finding largest volume, right? Largest, I want a maximum. So for the table method, I want this guy to be positive. It's going to be negative because I want it to be a positive gradient flat. Negative to give a maximum volume. So you can punch it in the calculator. I'm pretty sure that's going to be the case. But for me, right now, let's just shortcut and then go, therefore, max volume when x equals to root 50 over 3. Now they want dimensions, so they want me to sub this into the h value. So, and also h equals to, so if I punch that in, so I go 100 minus 4 times, well, square of that, so 50 on 3. Looks like 100 on 3, so square root of 100 on 3. And that is my final answer. So, once again, that's 4 marks. So, in terms of structure, that is, once again, to a T, right? Slightly more intense in terms of the derivation of things, in terms of differentiating, in terms of maybe even using Pythagoras, right? Some students don't see that, but a classic case of part 1, prove the formula. Part 2, differentiate, solve, test for max min, answer the question. How's that? Let's do, I guess, one more question, just to, I guess, illustrate the framework, and then next week maybe we'll do, or next lesson I'll do a few harder questions. So this one here, I mean, it's from James Roos, right, which in itself might signal a bit of difficulty. But also, you can see there's no real numbers at play. And the fact that, I mean, this is a James Roos question, and there's 5 marks for part 2, probably means that you've got to do a lot more, right? But classic framework, right? Part 1 showed that the area of the triangle is this. And once again, for those students that are quite cluey, looks like Pythagoras. Smells like Pythagoras, it probably is. Part 2 showed that the triangle maximum area is an equilateral. In this one, it's interesting, and that's probably why it's more marks allocated. And once you prove max area, and normally an easy question would say when x is blah, or when area, or find the maximum area is blah. In this case, show that it's an equilateral triangle. So once you find the value that maximizes the area, you got to then prove that it is that it leads to an equilateral triangle. So interesting. So to do this, what am I trying to do first? Now let's see if there's any words here that isn't on the diagram. So isosceles triangle AB equals that. That's not on the diagram. So I'm just going to quickly label that. Given that OM is X, that's A, and that's right angled, and M is a midpoint. So we got that. Yep. Show that the area of the triangle is that. So once again, it's a circle, right? And is R the radius? Yes, R is the radius, and that's not given as well. How can I use the radius right now, right? Is the key. So let's see. Let's have a look. So looks like if these guys are equal, I can use, I'm seeing Pythagoras in 2 triangles. I'm seeing so if I sort of, looks like that's the radius. I wonder if I use that one. Because there is another one, isn't there? The big top one that you can use. Right, where that's R as well. Yep, and that's R plus X. Let me see. So r squared. Yep, maybe I'll just use Pythagoras on the bottom. And I wonder, what am I trying to do? So let's find an expression for the area itself. So the area of this triangle is R. We know that, from our year 3 studies, that area of triangle ABC, let's denote it with A, is a half base times height. Now, in this case, let me put a box around this because it's ultimately very important. The base is going to be, now I'm going to let it be some other letter if that's okay. I'm going to let it be y, right? So that's y, and the height, if that's r and that's h, then that h is r plus x. Beautiful, and r is constant. Now, so it looks like if you look at what you want to prove, r plus x is already there, right? That's the h. Beautiful. Now I've got this extra letter of y when I sub that in, that eventually I want to remove. So here's what I'm going to do. Pythagoras kicks in. So off to the side, or over here maybe, I've got a triangle where it's r, x, and y. You can even, if your teacher's like, what's y, you can say, let bm equal to y, right? Just to work cleaner with a variable instead of just using bm all the time. Yep. So once that's the case, then I know that by Pythagoras, r squared equals to x squared plus y squared, which makes y the square root of r squared minus x squared, which is great because that's exactly what the second bracket is, right? All right. So let's see. Now, I've actually done a little bit of a boo-boo because the base, if that's y, then the base is actually 2y. Yeah? Which is nice because then the 2 and the half cancels out, so I get, therefore, my area is a half times 2y, which actually, it's 2. Now y, the whole purpose of this Pythagoras is to plug this guy into here. Beautiful. And then you have square root of r squared minus x squared, and then multiplied by r plus x. And I have what I want because the 2's cancel out. I'm going to flip the order so I can look like what I want. And there you go, my friends. We have part 1 wrapped up. Classic, right? Nothing too fancy there. I'll see if I can shift this up so I can buy myself a bit of space. All right, now part 2. I don't think there's anything fancy here. It's all, but I guess it's hard in that you're just going to work with very little numbers because it's capital R in this case, but hopefully that's not a showstopper. Let's have a look. Part 2. So I'm going to start with this. Let's differentiate. So remember, differentiate, solve, test for max min, answer the question in this case, prove that it's an equilateral triangle. Looks like another case of the product rule. So before I even differentiate, I need to get my tools ready. So u dash, that's simple. R is constant, right? Capital R is constant, that's just 1. V dash, bring down the half. Minus 1 to the power, so that's negative half, multiplied by derivative of the inside. 2's cancel out, so that becomes minus x on top. Bring this index downstairs to make it positive, and you get this guy as v dash, which then means that dA dx is going to be, let's have a look, u dash b, so square root 1 times that guy, plus, in this case, minus x times r plus x all over root. Feels very similar to the last question in terms of structure. That's my derivative, by the way. Yep. So point number 1, differentiate, done. Point number 2, let's solve. So just like before, bring this fraction over the fence. R plus x all over root r minus x squared Now this shouldn't be too bad. Times that up, square root goes away. So you got r squared minus x squared. I'm going to expand this to xr plus x squared. Move everything over. Yeah, move everything over. Feels like a quadratic actually, doesn't it? I'm hoping it can be factorized. Let's have a look. So you get 2x squared plus xr minus r squared equals 0. 2, 1 looks like it. So let's say 2x and x. Looks like r and r. Positive, so this guy's plus, this guy's minus. I think that gives me it. So I've got no more space down here. So what I'm going to do, I am going to copy this part. Next page. Plug it in. Okay, zoom in so I write a little bit neater. So therefore, I got r equals 2. Sorry, not r, I'm solving for x. X equals to r on 2, comma, negative r. Now, obviously, that guy's not true because r is greater, sorry, not r, x in this case, greater than 0. So I have my answer that I have to now test for Maxima. Now, my derivative is a monster. So it feels like I should use the table method, but just be careful because in using the table method, you're going to be, I mean, there's no value for r, right? So just keep that in mind. Just you're going to sub in fractions into that value. So I'll put it over here. So test for max min, which acts as a table method. So dA, dx. And just to be clear, I mean, if I have r on 2, yeah, in here, now I feel like if I put r in, I don't think you can, because if you put r in, that's when x equals to r. I don't think it's possible. Let's look at the diagram. If you put x as r, I think that sort of leads you to a probably equal to some number that is equal to 0, because when x equals to r, it's basically a radius and you have no triangle. So maybe a smart thing to do, because I'll be squaring everything, a fraction that is slightly bigger than this would be r on root 2. Now why root 2? Because when I square it, it becomes like 2, right? So when I plug this all in, it hopefully give me a nice answer. And then over this side, actually, I wonder, I'm just going to have a quick peek. If I sub in r, yeah, so you can see there, if I use whole number r, right, which is bigger than half, if I sub it in there, r, well, I'm missing a square there firstly. Yep, missing a square there. So if I sub in r there, then you can see that it's going to be erroneous because r squared minus r squared is 0, and you can't divide by 0. So I can't sub in. However, I can sub in 0, can't I? Yep, 0 would work for x. So let's have a look. So while I'm here, let me go back a slide and correct that fraction because I did omit the squared accidentally. All right, so when I sub this guy in, definitely 0. Yep, definitely 0. When I sub 0 into all the x values, I get that's r. All these are 0, so then I get r, which is positive, flat. And when I sub this in, I'm hoping it's a negative now. Do I want to maximize? Please tell me, yes, maximize, because I look like I'm going to be maximizing something. So just to be clear, when I sub this in, let's investigate that. Substitution. So I get, so subbing it in, I get square root of r squared minus x squared. Now, this guy squared will be r squared on 2 minus, looks like x times r plus x times r plus x. So r on root 2 on r plus r on root 2 all over square root r squared minus r squared on 2. Now, it was a bit complicated, but hopefully it cleans up nicely. So that's like square root of r squared on 2, which is r on root 2, minus, you know what? I'm just going to common denominator that. So that's just r squared on 2 minus, expand that, you get, sorry, when I say on 2, I mean root 2, don't I? Minus r squared on root 2, ooh, cancels, and then minus something else, r squared on 2 over square root of r squared. Let's clean that up as well. That's just r on root 2. Now, check this out. This is cool because I have a situation where this guy goes away. I don't really care what the final answer is, but for your purpose, the r squareds go away, and I sort of get like negative a half on 1 on root 2, which looks like, what's that, root 2 on 2? Negative root 2 on 2. I don't really care about the number, I care about the negative though, because that's exactly what I was looking for. So negative root 2 on 2, always negative, yeah. Therefore, max area when x equals to r on 2. So that's my third bullet point, right? Now I'm going to answer the question. So just to be clear, what did I do there? Differentiate over here, right? Got that? Looks a bit complicated. That's all good. Solve. Got that. Test for max min. Got that. Now I'm going to answer the question. So it's telling me to show that it's an equilateral triangle. So if I finish this question off by going, okay, what was my triangle for ABC? So A, B, C looked like that. I know that this was X and this was R. Yep. Now, what do I need to prove equilateral triangle? It feels like I need to do one of two things. I either prove all the sides are equal, or I prove all the sides are right angled. So I already know that the left triangle and the right triangle are congruent, right? I already know that this guy equals to this guy and this guy equals to this guy. Perfect. Now I've got R in. So it feels like I can maybe use trig. So many ways. Maybe I could use trig where I know that this was y, which I already found the value of. Actually, I use Pythagoras, so that's like r squared minus x squared. And I've got the side. So maybe I'll use Pythagoras to determine the value of this. Yeah, maybe I don't even need trig because I know I got this as y. I can find the value of this using Pythagoras and then set all three sides the same. Perfect. So I know that, let's call AB. So AB squared equals to y squared plus r plus x squared. So y squared would be square root r minus x, r squared minus x squared, squared plus r plus x all squared. Let's expand everything, please. R squared minus x squared, squared plus 2rx plus x squared. Beautiful. X squared goes away. You got, is that what I want to see? 2r squared plus 2rx. Is that what I want? Because I can take the square root of that. Is that what I want? Let me have a think. Because if that's the square of that, then I want this guy to be 2 times that. You know what? I'm not going to do it this way. Pythagoras, I think I can carry that forward, but instead, can I just use that right angle triangle here? Yeah. And I'm just going to use, let me see what I can use. I've got R on 2, maybe I'm thinking, maybe just 10. 10, let's see, BN. Yeah, let's just do all that. So, oh no, actually, I was very close, wasn't I? I was very close because I forgot to sub in x equals to here. Yeah, maybe I'll do that. Maybe I'll do that. Then I get 2r squared plus, what's that, r squared? That's 3r squared. Okay, so therefore, AB equals to root 3 of r. So I've just found that this side is root 3r, which means because they're equal, this is root 3r. And I'm hoping that when I sub this in, does it give it to me? Yeah, I think so, r squared. It's a quarter. Does it work? Let me see, let me see, let me see. I'm very excited, let's see. This side here. Okay, y equals 2. So that's, I'm after 2 y's, right? For this whole side. 2 times y equals to 2 times root. See, 2r squared. Okay, r squared. Minus r2. That doesn't look that great. That doesn't look that great. Am I missing something? So let's have a look. 2 root. This is going to be r on root 2. Oh no. Look at that. That's root 2r. Oh no. What did I do wrong here? What did I do wrong here? Let's see. R squared. You know what? Let's try. I'm going to take the same diagram. Use tree. I'll come back to this actually. I'll come back to this because I really want to solve it. So if I did by trig instead, this is why it's worth 5 marks, I guess. So this is r plus x, and this is just square root of r minus x squared. Now I know that x is r on 2, so that's like 3r on 2. And I know that squared there, and that is going to be square root r squared minus r on 4. That's why, sorry, I got it. In doing this way, I've actually got it. So it's down here that I made a silly boo-boo. This bit here. Because then there's 2 square root r squared minus 1 on 4. So it's like r squared on 4, which is 2 and 4 goes away, root 3. So I've got all 3 sides equal to root 3r. I can conclude. Don't you love maths? Here you go. I can go, therefore, do it in blue because I've been doing everything in blue. Therefore, AB equals to AC equals to BC, which is root 3r. Therefore, triangle ABC is equilateral when r equals, when x equals to 2. All right, we got there. Well, I got there. So in this question, the difficulty was actually the very last bit, once you get x, to then prove that it's an equilateral triangle. So I hate to say it, the calculus itself fits right to a T into the framework. And it's just probably 1 marker at the very end, once you basically found the value of x, to then prove that it's equilateral. That sort of caused a bit of grief, but hopefully that was a good demonstration of the Maxima Minima framework, where part 1 proved the equation that you have to differentiate, and part 2, the 4 points: differentiate, solve, test for max min, and then in this case answer the question, which was quite painful, but we got there in the end. Guys, I hope you liked the video. If you do, give me a like, get a subscribe on. I'm planning one more video on Maxima Minima to basically show a few more difficult questions, and hopefully that concludes it. I'll see you guys next time. Cheers.